Okay, so good morning, Washington. Morning. So I'm Thomas Clark, and this morning I'm come to you from the Wigner Research Center for Physics in Budapest, Hungary. I'm not Hungarian and I'm not American, but I'm sure you can forgive me for that. But so naturally, though, coming from a physics background, I want to talk to you about scientific closure. Okay. So what is scientific closure? Well, we like to go to definitions, and so we can say, well, what is science? And of course, there's a lot of different ways, you can answer this question. Maybe, yeah. So it's maybe a little bit dangerous to ask a physicist to define what science is. But if it makes you feel better, actually, Rutherford, he got his Nobel Prize in chemistry, just for maximum irony. So what is the next question? So maybe, what are scientists actually rewarded for? Maybe this is a more honest way of working out, what science is about. And actually, I had to think about this, and I came up with, scientists are rewarded for new, testable knowledge. And so maybe this is a little bit different, to how people think about the sciences. And actually, if you want to maximize the reward in science, you actually want to maximize the newness, which means that science, or good science, is measured by the level of surprise. And so to give you an example of surprise, there was a crazy scientist at the Clojure last year, and he pointed out that if you look at the fundamental patterns in the universe, you have laser patterns, then the next level is brackets, and then the next level is, putting stuff in between, which, I thought was an interesting result, also a bit surprising. But my point here is that, science is not actually so much about certainty, is that it's about discovery. And so for my purposes this morning, I want to define science as systematic exploration. Okay, so what is the next question? What is Clojure? They say you should know your audience. But I'm not going to answer this seriously, but for my purposes, I just want to say that, Clojure is a top-level language for integrating things. And, I could say this in the sense, Clojure is powerful, and, it's competitive, and in that sense, top-level. But actually, I want to focus on the idea that it works very well, in my opinion, at a very high level of abstraction. And this brings me to this idea of a bird's-eye view. And so this morning, I kind of want to talk about, what is available for science as a whole. And, I put this kind of warning in because I can't demonstrate science as a whole. And so in this talk, we're going to have to be quite general. I know that Clojure people like interactive demonstrations, and Karen was putting me to shame in the last talk. But I don't have time for that, so I'm just going to run through the big picture scene. But actually, to make it more interesting, maybe rather than a bird's eye view, since we're in Washington, maybe we can say the eye of providence. So we have... So where to start? If you want to do something sciencey with Clojure, then, well, I was thinking about this, and I think the answer is actually very simple. I think you should steal something. Because, I think this is actually a solid design principle. Whenever you're starting a new company or you're starting new software, you don't want to reinvent the square wheel. You want to build on something else. And actually, there's a lot of advantages to this. There's little cost, naturally, but also you can gradually integrate, your old workflow into your new Clojure way of doing things. And the reason I mention this in particular is that, scientists are not developers. And so, they want to be able to rely on the libraries that they've been using for like 20 years. And so you need to remove the fear of loss before you can attract, more scientists into the Clojure ecosystem. But of course, as we know, Clojure is pretty much available everywhere now. But in particular, when it comes to scientific languages, which people use on a kind of everyday basis, the interop story with Clojure is very good. And this is something that I want to highlight. As a very biased example, and I can justify this bias by saying that, science should be new. And so I'm very happy to announce that we now have Wolframite 1.0, which is a bridge between the Wolfram language and Clojure. And this was something that was funded by Clojurists together at the beginning of the year. But for those of you who are thinking this sounds a bit familiar, you're not wrong. In fact, going way back, 2009, there was actually a bridge between Clojure and Mathematica. But it's fair to say, I think, that it died, somewhat. And so we're very pleased to announce that it has been, resurrected recently. Okay, so why should you care? Well, when it comes to Wolfram specifically, it's been around for more than 40 years. And it really is the kind of world-leading system for dealing with equations. And so for a lot of people in the sciences, this is important. And maybe for yourself, maybe you're not working with equations. But actually, Wolfram, in its 4 decades, has really expanded a lot. And so now if we look at the horse's mouth, so to speak, Wolfram sells itself no longer about its equations, but by saying that what it offers is high-level functions to enable people to quickly express complex ideas, in whatever computational form. And it's worth mentioning that Wolfram now has more than 6,000 functions in its core namespace. And it's actually the most expensive Lisp without a REPL. And so, of course, we, in its heart, you realize that actually it was built up from an early form of Lisp. And of course, we can't have this, so we have to do something about it. So just to give you an idea of what we mean by high level, and so here's an image from a somewhat famous psychology experiment. And we're identifying people as important. But actually, in the Wolfram language, if we just have a single function, this image contents function, then what does it do? Well, it looks at this image. It uses its machine learning algorithms, its understanding of concepts like persons, and then it breaks up the image into these persons with all the graphical information and the probability. It lumps it together in a data set, and it returns this to you in one type. So, single function. Wolfram is pretty high level. And just to give you an idea, of what Jakob and I have been working on this year, a big part of what we've been doing is customization. And so, I do work in, the physical sciences, so the equation part is important to me. And so, yeah, we've been working on, rather than a lot of magic that was happening previously, now we have the ability to pass in options to the actual runtime system, which means that you can customize Wolfram in a sort of live or at least runtime-based way. And so the idea here is that we don't just want to be able to use Wolfram libraries, but that we actually want to combine the best of Wolfram and the best of Clojure to make something potentially better. And so here, for instance, we're using the fact that Clojure supports Unicode symbols, even though Wolfram at heart doesn't. And so we can create our nice mathematical expressions in a mathematical way. And this is sort of part of a bigger picture where recently, apart from getting things working, that we have been working on the user experience so that you can call, Wolfram functions as if they were Clojure natives. And this includes the custom symbols that you can define yourself and keep them for your next session. And we get to use threading macros. It seems like such a small thing, but actually when you're dealing with 20 lines of equations, being able to break things up into individual components and read through it in a natural reading order actually helps in a surprisingly meaningful way. Okay, so that's Wolfram. But now I just want to give a quick mention that not all of the interop in Clojure is new and experimental. In fact, some of the interop is just old and boring, in the best possible way. And so I'm not going to say much about the Python interop. It just works. But I do want to mention it for another reason, because last year, I made a promise that I would write a paper, that I would rewrite this Python library for taking data in the lab. But the trick was that I would do it in a kind of Clojure data-oriented way. And so here it is. I'm happy to say that I fulfilled this promise. And here you can see just how easy it is to integrate with Python. There's one call to tell Clojure where everything is, and then you can just use your familiar libraries and then your new, not familiar libraries, and that's it. No further ceremony. But then you might want to, you might be thinking, well, why did I want to, rewrite a Python library in a data-oriented way? And actually, the true story is that we inherited a bunch of software from our German colleagues. They had paid for a Python map onto the language which was used to run the experiment. But in programming terms, they sort of warned me that it had a sort of undeclared dependency on prayer. I'm in favor of praying, but I don't think they were. And so this really points to a kind of real-world need for scientists to understand, how to maintain their code and how to write code that's going to last, more than 10 minutes, particularly if you want to change something. And just, this is probably a familiar book to people. It came out a few years ago by Hansen and Sussman. And the main premise of this book is that flexibility is a neglected dimension. And I'm sure this is familiar to many of you here. But for me, it was interesting because if this is true for software developers, then you have no idea how true it is for scientists. And this is particularly relevant because in science, as I mentioned, newness is very important. And novelty is so much more important than stability or reliability. And so, we need to learn this lesson, that it is better to model for the unknown, and so structure programs such that new situations are dealt with by adding new code rather than changing existing code. Okay, but I'm sure this is familiar to you, but I just want to point out how deep this goes. In fact, if we go back to your wallet, I just want to point out, maybe many of you know this, but I only just found out. So this symbol, it was very deliberately chosen. And the idea of this symbol is that you have this unfinished pyramid stuck underneath the Eye of Providence. And the idea is that the founders believed, founders of the US, that is, they believed that they had created a system which was well enough designed that they could add to it. So there were 13 steps, for the 13 states. And of course, historically, there are now, it was proven true. There are now more than 13 states. And so it was a confidence in the design of their flexible system that this symbol was put on the money, at least as far as I know. But the interesting thing is that, I'm not American, so I'm willing for you to correct me. But what I can tell you is that this goes even deeper. In fact, if you go all the way down to the level of quantum mechanics, then what you find is something quite interesting. And maybe not everyone knows this about quantum mechanics, but there was this really important discovery that the future does not emerge from the past. And so, what I mean by this is that the future is fundamentally, not just practically, unpredictable. And I felt a bit bad about this because this morning there was a lot of talk about deterministic workflows. I'm sorry, but it's not going to happen. And the idea is that if the universe itself is fundamentally unpredictable, then your perfect program is going to have to change at some point or another. And actually, this is one of the things that I really like about the Clojure programming system, is that people take this idea of flexibility very seriously. And it gives me confidence that Clojure will move on into the future while still being Clojure. Okay, so maybe that was a bit airy-fairy for lots of you. So I want to make a practical example. I want to talk about plotting things. And so plotting things is quite an important part of science. And so for those who don't know, this is the Higgs boson, as far as we know. And this was quite an important, this was an important discovery, but it's always been a big, pet peeve of mine that plots are dead. It's a sad fact, but you can't ask questions of this plot. You can't change it. You can't update it. In no way is it flexible. You could go far as saying that it is X data. But the really annoying thing about this is that it's still, this is the default, the standard in the sciences. But in the programming world, I'm happy to see that data science in particular is driving a real change to this idea of how you plot things. And so a good example of this is the Vega system. This is over many years they've been developing a grammar of graphics, and of course they took to heart this idea that the fundamental abstraction when you're moving between domains is just data, and so when it comes to describing systems, they just use JSON maps. But of course, like the pyramid analogy, this works so well because you can just add layers upon layers until you get a visualization which is easy enough for you to use in everyday life. But when you want something more complicated, you just drop down to the other layer. And of course, rather than just being suited for long-term flexibility, now this kind of data-oriented plotting is also very good for short-term flexibility. And so these plots, I hope if it works, are actually interrogable. Ah, there you go. I was worried it wouldn't work. And so you can see here that these plots now, because they are just data and that because they maintain the source code inside the system when it's embedded in HTML, you can actually play with things. And this is a much more natural way of dealing with data in the sciences. And of course, once you realize that your plots are just data and they're just maps, then of course there is a good language for playing with that, and that is, of course, Clojure. And in the sort of scientific Clojure community, for a while we've been using this Hanami library, which is different because it doesn't try and create lots of functions, but actually it's just about transforming data. Okay. But of course, that was just the beginning. So in the Clojure ecosystem, there's been a lot of kind of growth in these visual tools. And so if you want to plot data sets, we were using this Hanami system, but this is being extended. Also the Plotly specifications are now becoming very popular, and there's a growing movement in the community to build this table plot library, which is about integrating different options into a single library. And so if you have also very mathsy plots, then there are some really nice things being done by Sam Ritchie. And so here you can see that we still have interactive plots, but they're more suited for plotting individual mathematical equations. Okay. So as much as plotting things is actually important in the sciences, particularly if you're working in the numerical sciences, at some point you want to calculate something. And so, what about Clojure? Can we do this in Clojure? Because I've already mentioned that, Clojure is very good at interop. It might have something to do with the fact that the entire language is in itself in a data structure. But you might be thinking, if Clojure is so data-oriented, then why do we need interop at all? And of course, the short answer is we don't. And so I'm very happy to say that, as an example, if you want to remove the Python from your everyday data science life, then really the libraries you need to replace are NumPy and SciPy and Pandas. And these now can actually be pretty much replaced by dtypenext, fastmath, and tablecloth, which is an API on top of TechML dataset. But I don't want to give you the wrong idea that these Clojure libraries are actually covering a much kind of wider scope of problems. So in that sense, they're kind of over-defined replacements. And so just to give you an idea, so dtypenext is at heart actually a functional interface to memory. And then at a higher level of abstraction, this means that it's actually the basis of a lot of the language bridges to Clojure, Python and Julia being good examples. But then at the next level of abstraction, because it is good with working with tensor data, then it is a drop-in replacement for NumPy. But it's Clojure and fast. So the fastmath library, in contrast, is more about the maths part of the SciPy stack. So if you're used to using functions in the kind of Python, Julia, or R ecosystem, then fastmath is kind of aiming to supply these in a nice, usable way. And I'll say a bit more about this later. But just to give you a bit more of a zoomed-in example, I think I'm very excited about this tablecloth library, which was actually mentioned briefly earlier. And just to summarize, so tablecloth is, roughly speaking, feature complete with pandas. But I think it's actually better because it has larger than memory data. And I feel like it integrates with Clojure more than pandas integrates with Python. And so, I can prove this if we look at the pandas documentation, which seems like a fair place to look at these things. What you find is that when you're wanting to query something in your data frame, there are actually quite a lot of different ways to do it. And in fact, what you end up having to do is use lots of these little micro languages, which themselves are not really Python. And in fact, if you want your query to work for all of your data types, you end up having to write like strings within strings, which is, yuck. So in contrast, tablecloth is a bit different. If you take this entirely hypothetical example that you wanted to make a tree plot for a talk that you're giving in Washington, and you realize that the Vega spec is quite a weird data format, then what you can do is you can create your little graph, make it a data set, and then drop to another language to process your data. But the interesting thing here is that this is not strings within strings, and it's not some weird micro language. Tablecloth is a Clojure library, which expects you to know Clojure, which seems fair. And voila, this is your little tree plot. OK. So what is quite exciting, though, in the scientific Clojure space at the moment is that there's a lot more to life than just working with data sets. And actually now, whether you want to do data sets or images or numerical maths or symbolic maths or linear algebra or statistics or Bayesian inference or machine learning or deep learning or LLM or OpenCV, then actually, Clojure's got you covered. There's a lot of kind of mature libraries now working in this space. And of course, if you don't, if your needs are outside of this area, then you can always fall back down to interop, with just another layer in the pyramid. And so I think this is it's a very exciting time in the scientific Clojure community. And so yeah, just to repeat this point, it's like, we have a lot of options now. And we're no longer dealing with just a couple of libraries. We're dealing with an entire ecosystem. And so, this is a really good thing to have, but it does bring some problems. Like how do we unify, all of these diverse libraries? Maybe I know what you're thinking. Clojure doesn't do frameworks, and in general, yeah, I really agree with this. I think it's a really good approach to maintaining this flexibility. But we still have to deal with the problem. Integration is still a real problem. In fact, particularly scientists are not developers. If your plotting library and your dataset library don't communicate, scientists don't look at the source code and work out how to fix it. They just use something else. And so we need to solve this integration problem. And so the real question is, how do we reimpose order in this ecosystem without losing the underlying flexibility? Or to put this another way, is how do we stop this from becoming this? And yeah, and for me, and for the little community, I think what was actually, I want to apologize when I say we. It's a very much something of a royal we, because I wasn't really involved in the scientific Clojure community in the last year. So all credit to the guys who were doing this work. But just to say that when you're coming to approach this problem, it's not actually just a software problem. It's a real-world problem. And so if you look at the real world, we don't want a tyranny. For other reasons, it's not flexible. We don't want chaos, because nothing talks to each other, nothing connects to each other. And so what do we do? And so the answer, I think, with my obligatory Lord of the Rings reference, or even in the Second World War, the answer is, I think, voluntary cooperation. A very huggable moment, I know. But, and so out of this realization, comes this Scicloj community. Personally, I don't really like the name. Maybe I would have went with Psycho, but maybe that's just me. But in the last year or so, the Scicloj community has been thinking a lot, I think, about this integration problem. And one of the realizations they made is that you don't actually need a single interface, to cover this whole space of scientific Clojure, because there's a lot of different domains, there are a lot of different things to calculate, and you'd have to learn the individuals' parts of the libraries anyway. But what you do need to know are which libraries to use, which work well together, which ones are likely to be maintained, and how to structure your general application logic. And this is where this library Noj comes in. For wordy people in this audience, I think actually Tim mentioned yesterday that Noj is actually the short version of Clojure, which stands for the North Star, which is the kind of guiding light. And this goes back to this idea of science being about exploration. And so this project, interestingly, at the moment, has declared that it doesn't really want to offer more code. The Noj project is more about creating a dependency stack so that if you copy a deps EDN, then all of these libraries just work. It wants to do integration tests, provide a set of organizing principles, and documentation, lots and lots of documentation. As well as, and maybe I'll come to this later, tutorials which are in themselves actually tests. As well as, you do need to write some code, but these will be in kind of subsidiary libraries, which really are just small adapters. Okay, so to give you an example of this integration in a kind of real-world space, I want to look at this thing called visual tools, which is another big growth area in scientific Clojure, or just in Clojure in general, actually. And the main idea here is that the REPL is more than printing lines. You want to be able to visualize any kind of data type. And I don't know where he is, but Chris talked about this yesterday when he was talking about Portal, which was a really nice option. But actually, also more than just a REPL, we now have this kind of idea as namespace as a notebook. So you want to be able to write things in a well-organized way, like in a Clojure namespace, and then export that out to whatever human-friendly format you need, so that you don't need to write two things. And so when coordinating between all these visual tools, this is an adapter that Daniel Slutsky has been kind of pioneering, is that, how do we view the outputs of all tools consistently even, without restricting library creation? And the idea of the Kindly library is that each visual tool kind of implements some very light specifications. And when I mean light, I mean just associating a type with a name. And then when the user goes to mark up their namespace, they just have to add a tiny amount of metadata, and then the visual tool will know which thing they're trying to plot or visualize. And so just to give you an example, so if you are in your namespace and you want to put a markdown comment, then you just drop in a little bit of metadata which says this is markdown. And then when you export this to some other format, like a presentation, then the visual tool knows how to interpret this. And yeah, this is just a kind of suggestion that, that although this is voluntary cooperation, it is a strongly encouraged convention. There'll be much judgment for people who don't use this in the future. And so just to give you an example of one of these visual tools, I want to talk a little bit about Clay. And so the basic idea here is that Clay is a lightweight compromise for everything. So it does this kind of visual REPL evaluation of individual S expressions, but it also does namespace conversion, and it also links to Quarto. And so Quarto can be used to export to many other different formats. And so you can create HTML books or even HTML presentations. And so it'll be no surprise to you, this entire presentation was just exported as a Clojure namespace, or from a Clojure namespace. And actually, something that I've found quite useful recently is in making documentation using Clay. And maybe I will, can I show you? Aha, there we go. And so here, for instance, are the documentation, or is the documentation for Wolframite. And so the idea here is that you just write a Clojure program, and so all of this code is just real code in the namespace, which then the evaluation is printed into the HTML. And the nice thing about this, and maybe this is common amongst developers, but it's certainly not common amongst scientists, that by generating your documentation from real running code, then actually all of your documentation also becomes a test. And so if your documentation works, your tests work, and if your tests work, maybe your program works. So yeah, it's an efficient way of doing things, I think. Okay, so I'm coming towards the end. We're not there yet, but I couldn't let you go without doing some real science. So I'll paint you a picture. Picture the scene. You're sitting in your office, and someone drops some simulations on your desk. And you're like, great, we've got new data. But actually, it's dead. So for those who don't know, simulations are really the bitmap of the physics world, in the sense that you have the answer, but you don't really have any information. We know that there are some laser beams that look like this, but we don't know why or how we can model this. And so we want a model. So what do? Well, we do what any self-respecting scientist does. You ask Wikipedia, and you have a look around, and you find some familiar physics, which is different, but has some familiar-looking patterns. And then you say, oh, OK, so this looks useful. But how do you then turn that into code? And it's like, well, there's a problem. It's like, this is also dead. And so there's a lot of scope for improvement in the future. So this is just a picture of an equation. So how do we undeadify this equation? And what we mean by this in practice is how do we turn this into something that you can play with symbolically? And actually, in Clojure now, we have options. So we have Wolframite. But we also have this library called EMI. And so for me, EMI is a great hope for the future because it's a sort of pure Clojure and ClojureScript implementation of symbolic maths. And yeah, I think it's a really exciting project for the future. And so just as an example, I can say, well, I looked at this equation, and it looks like it's using complex numbers, which is not so much fun. And so can we use EMI to simplify this? And yeah, it turns out for our purposes that if you substitute in some equations, then actually the equation is real. OK, which is fine. So what do we do next? So we have this equation, and we've simplified the equation. So how do we use it? Well, you look at the symbols, and you realize that one of the things is an insert polynomial. And what is an insert polynomial? And you might think that, OK, the physicists should know. And it's like, no, because this is obscure, even by the measures of mathematical physics. And so there's no Wolfram function. There's no NumPy function. So what do we do? This is a true story. And so it turns out that if we go to the new FastMath library, it actually has polynomials. But it doesn't have the insert polynomials, kind of unsurprisingly. But it turns out that if you ask generate me nicely, do the polynomials even exist? He'll do something about it. The new version now has insert polynomials. And so, FastMath 3, I should mention, is also just coming out. If it's not already released, it's in the process of being released. So it's a very useful library. Yeah, and happily, it now has your favorite polynomials. And so, well, what happens next is that once we have this kind of fundamental maths function, we need to turn this into a function that we can use. And actually, if you discount a lot of the definitions at the top, then it's actually very nice. You just have to write a function of 2 dimensions, and here is the equation turned into a program. And after this, we can use the kind of magical functional interface to memory that dtype next is. There's no for loops or vectorization. You just have to pass in your function, and voila, you get an image of some nice laser beams based on a real model. OK, so this is a very short demonstration, but maybe it can go some way to convincing you that you can do science in Clojure. But it wasn't actually any good. And so one of the things which for me was very nice was that you could see there was a very clear transition from equation to code. In the end, you're just dealing with a function. The function looks like the equation. There's really not much going on. So originally, actually, I did find an implementation of these laser beams in the metadata of an academic paper, which was written in Python. And it was hundreds of lines long. I had no idea what was going on. And that was one of the reasons why I had to ask generate me whether there was some better option. But actually here, it's a few lines. It looks really nice. So it's a big win. It's readable. But actually, this was a bit of a surprise to me. It was fast. I thought that the price of being so readable would be that it would be slow. But actually, it was very fast. It was in the milliseconds or something to produce, which is fine for me with my slow reaction time. But actually, I thought this was fine. But of course, generate me, despite, I didn't ask him to do these things. He became very involved. And so he was like, no, we can use type hints, and we can make it much faster. And you might think this is a bit of a trick. It was like, well, OK, it's a dynamic language, but then you're adding type hints. But actually, being able to solve the problem or being able to learn how to understand the problem before you put in type hints is actually a big win. Because it's easy to put in type hints once you understand the problem. If you don't understand the problem, then everything just becomes much more complicated. And so it's so fast that actually it was very nice that we could play with it in the REPL. And also we could use this new optimization that's available in FastMath to check whether this was a good model. But I don't have time to talk about that. Yeah, and so you might be thinking, okay, maybe this is a very artificial problem that you came up with for the sake of a presentation, but actually no. I hope that we'll publish a paper about these nice laser beams very soon. Yeah, and so that's my little overview of the sciences. But I think I have a few minutes left, so I want to say something nice about you, so hang around. Because you might be thinking like, okay, maybe how did this happen? Is Generate me like my best friend, and therefore it was easy to just ask him to do things for me? But the truth is, I'd never met him before. I just posted a message on the kind of Zulip community, and he really went the extra mile. And you might think, okay, well, this is a once-off. But actually, I asked last year about whether a function existed, and GSA kindly, having looked at it for a bit, was like, I'm sorry, you're going to have to roll your own, I'm afraid. But then, 4 minutes later, he then gave me a solution. So I don't even have time to respond. And so, yeah, this seems to be the kind of de facto measures of how people work. And so, as you know, like I'm not a real programmer. This is my first programming community. And yeah, it's actually very amazing. And I just wanted maybe to mention that, there's a lot of talk in general about, and there are a lot of reasons why you might want like a very big community. But actually, there are benefits of being a small community, and that's something maybe, yeah, to appreciate. Okay, so in the Scicloj community, there's a lot going on, whether it's lots of meetups or book studies or mentorship, as well as, also private projects. There are lots of public projects, but also, I have lots of ideas. So if anyone is interested in wanting to do something, then, just give me a shout. If you want more information, then Scicloj has its website, and there are these talks which go into more details on particular examples, which you might find interesting. Or get in touch in the kind of usual ways. Some people like to use Slack. I don't know why, but you can get us on. Zulip is where the kind of sciencey data science people seem to live. Yeah, so please get in touch. So yeah, maybe just before I close, I just want to say that, well, what is the surprise, in this talk? I said that good science is, measured by the level of surprise, and maybe it's not that surprising that, Clojure is good for the scientific calculations and processes. But actually, I did discover something when I was preparing for this talk. If we go back to our new equation of the beams, we can see that the brackets are still there. But if you change one parameter over and over, then what you find is that the eye of providence was there all the time, watching us, sort of thing. So thank you very much.